this lesson, we introduce the concept of random variables and some useful function for the computation of probability. A random variable is just a numerical value associated to the outcome of an experiment. Just to fix the idea, imagine your experiment is tossing a coin. You have just two possible results, head or tail. And we can associate, for example, two different numbers to the different outcomes, for example, 1 and 0 for head and tail. And in this case, our random variable is can assume just two values, 1 and 0, with the same probability, 1/2. There are a couple of very useful functions associated to these random variables that are very useful for the computation of probability. The first function is the cumulative distribution function, and it is defined as the probability that the random variable x is less equal a. A is the parameter of or independent variable of the cumulative distribution function. There are three main properties of this function. First of all, the cumulative distribution computed in -infinity is 0. And this is obvious if you look at the definition, because the probability that x, the random variables, is less than -infinity is actually 0, impossible. The same for the opposite, plus infinity. The probability that the random variables is less than plus infinity is 1, because it is always the case. And as a matter of fact, the cumulative distribution function is a non-decreasing monotonic function. The second important, very important function that we can use to compute probability is the probability density function. And it is defined as the ratio between the probability that the random variables is within this interval, infinitesimal interval, between a and a plus the a. The a is an infinitesimal interval, divided by the a. Actually, if we look at this probability in green over here, we can see that the probability is the area that is under the function, the probability density function, in the interval, infinitesimal interval, dA. There are four main features of this probability density function. The first one is obvious. The probability density function cannot be negative. And as a matter of fact, we come back to the definition. This probability density function is a probability, and as we have seen already, this probability cannot be negative. The second one is that the probability density is the first derivative of the cumulative function. And this can be demonstrated quite easily. In fact, if we consider this probability that x is within the interval a and a plus dA, we can divide this into the probability that x is less than a plus dA minus the probability that x is less than a. You see that in this plot over here. If we divide this difference by the infinitesimal interval dA, we get exactly the definition of first derivative. And so probability density function is the first derivative of the cumulative function. Third property is a direct consequence of the second one. Since the probability density is the first derivative of the cumulative, this means the cumulative is the integral of the probability density. And so if we integrate the probability density function between a and b, we get the probability that x is less than b minus the probability that x is less than a. Those are the cumulative integral of the probability density function. And so we have the probability that x is within the two numbers a and b. So remember, the probability that a random variable is within this interval a and b can be computed just by integrating the probability density function between A and B. The last property is an obvious consequence of the third one. The probability that the variable x is within the interval minus infinity to plus infinity is 1. And this means that the integral of the probability density function is always 1. Or if you want, the area under the probability density function is 1. Remember, this property is quite useful to avoid errors in computation of probabilities. But let's come to an example of a continuous random variable. A continuous random variable is a random variable that contains continuous set of values, real values. The example is this one. Imagine to have a marble that is moving with constant velocity along a track L meters long, and our random variables with a constant velocity, and our random variable x is the position of the marble along the track. And of course, there is no reason why this position is different from another. Now, if we look at the cumulative probability function, that is the probability that the variable x, that is the position of the marble along the track, is less than a, well, this is proportional to a divided by capital L. And it is within the interval, of course, 0, capital L. That is, the cumulative distribution function is just a linear ramp here going from 0 in a equals 0 up to 1 in a equal L, and then stays constant 1. The probability density function is just the first derivative of this one. And so it is a constant between 0 and capital L, and the height of this constant, the level of this constant, is the slope of this line here, that is 1 over L. Now let's see another example, different, because we are talking about discrete random variables. That is, random variables that can take only a discrete set of values. And as an example, we can use the number on the top of the face of a die. We know that we have just 6 possible results, integers from 1 to 6. And the cumulative distribution function is this one, this funny step function here. We can justify this function in this way. Remember the definition of cumulative function, distribution function. The probability that our random variable is less than 1 is of course 0, because our results, our outcomes, start from 1 up to 6. The probability that the random variable x is less than a number 1 from 2 excluded 2 is just 1 over 6, because we have just one result that is successful in our experiment. If we look at the value of the cumulative distribution from 2 to 3 excluded 3, we have just 2 possible outcomes, and so we have the values 2 over 6 of probability, and so on, and we go in steps up to 1 at value 6. Now the problem is, since we have this step function and we would like to compute the probability density function, well, there is the problem of the first derivation of this function where we have these discontinuities here. And we have not a mathematical tools in order to compute this first derivative in correspondence of the integer numbers, in correspondence of this jump here of the step. So we have to introduce a couple of funny functions. The first one is the step function. Simply, the step function is a function that is 1 for a greater than 0 and 0 for a less than 0. We do not define, it is not important, the definition of the step function exactly in 0. But we have this, you see this jump here in position 0. The second function is the Dirac delta impulse function, defined as the limit as t goes to 0 of this rectangle here from minus t over 2 to t over 2. And notice the height here is 1 over t. Notice that the area of this rectangle is always 1, whichever is the value of t. And so for t, capital T, going to 0, this rectangle here becomes a very sharp function, very high, infinity, and but the area is always 1. And so this delta function, this very strange function, is represented with the symbol of this arrow here, where the height of the arrow, 1, indicates not the amplitude, which is infinity, but indicates the area of the function. Now, it is funny to see that this function here, delta, is just the first derivative of this step function here. And we can show it in a minute. This is the definition of delta. And it is quite clear that this rectangle here can be split into this difference. That is, the step function anticipated by capital T over 2 minus the same step function delayed by t over 2. The height of the step function is multiplied by 1 over t. And if we write down this difference here in this formal way, you see that we have written here for capital T going to 0, going to the infinitesimal value, we written down exactly the definition of first derivative. And so delta is the first derivative of the step function. So now we have the tool to compute the first derivative of step functions of discontinuities. And if we look at the cumulative distribution function with, you see, many jumps over here, and we compute the first derivative of this step function in correspondence of values 1, 2, 3, 4, 5, 6, we have this step function of height 1 over 6, and so we have impulses in position 1, 2, 3, 4, 5, 6 of area 1 over 6, and 0 everywhere, because you see that the function, the cumulative function, is flat, and so the first derivative is 0. Notice that the sum of all these areas is 1. That is, the integral of the probability density function is 1 as always.